So this is our last video on simple harmonic motion. Let's go ahead and look at example number 4. A ball on a spring is pulled 6 inches below its rest position and then released. So if rest position is equilibrium, the ball is pulled 6 inches below. So here's equilibrium, so it's pulled 6 inches below. Then it is released. The period for the motion is 4 seconds. Write the equation of the ball's simple harmonic motion. So as you go through this process to write the equation, you want to ask yourself a few questions. Is the spring released at the amplitude or the origin? And if it's pulled down below the rest position and then released, then we would say that it's released at the amplitude. Now I want you to think about the importance of that. You know that this is either a sine or a cosine function. You know that cosine always begins at the amplitude and sine begins at the origin. So you know that this tells you that this is a cosine function. So far we have d equals a times the cosine of omega t. Okay. Next, is the spring pulled above or below the rest position? In this case, it's pulled below, so that tells me that a is going to be a negative value. So I know that a is negative. How do we know the value of a? Well, we can look and see how far the ball was pulled. It was pulled 6 inches below rest, so a is -6. We were given that the period for the motion was 4 seconds, so one full cycle. It took 4 seconds to complete that cycle. So let's use that to find omega. So if the period is 4, then 4 times omega equals 2 pi. And dividing by 4, omega is equivalent to pi over 2. So our equation is -6 cosine of pi over 2 times t. And the importance of having this equation is now we can answer some other questions. We can find out the distance or displacement at specific times. For example, if we wanted to know the displacement at time equals 4.3 seconds, we can plug 4.3 into t and solve for that displacement. Example 5. An object in simple harmonic motion has a frequency of 1/4 oscillation per minute. So the frequency is 1/4 oscillation per minute. And an amplitude of 8 feet. So I know the absolute value of A is 8 feet. Write an equation in the form d equals a sine omega t. So we're already given that this function is a sine function. If the amplitude is 8, then I know that a is 8 times the sine of omega t. So I'm kind of getting a little bit of ahead of myself. It says find the amplitude or the maximum displacement is 8 feet. Use the frequency to find omega. Recall that frequency is the reciprocal of your period. So if period is, let me back up. So if frequency is 1 divided by the period, then we can say that frequency is 1 divided by 2 pi over omega. And we can keep it, switch it, flip it, and the frequency is omega divided by 2 pi. We were given the frequency as 1/4, and now we can cross multiply, and omega is pi over 2 again. So our equation is d equals 8 times the sine of pi over 2t. So the last thing I would like for you to do is to go back to the first page of your notes. And I'd like you to use what you've learned to write two equations. For the first equation, I'd like to know, and I'm not talking about the buoy, I'm talking about the spring here. You were given that time is t equals 4 seconds. And so I would like you to write an equation for the displacement starting at equilibrium and I'd like you to write an equation for when the displacement begins at its maximum positive displacement. So using the fact that t equals 4 seconds and this figure, write an equation when the ball starts moving from equilibrium and a second equation when it starts moving from its maximum positive displacement. If you'll write both of those equations on a sheet of paper showing all of your work with your name and turn it into the tray in my classroom tomorrow morning or the next time when you get to class, I'll give you a bonus point on the next quiz. So it is due at the very beginning of our next class meeting.